Between that
Hey there, everyone. We're going to get underway. So this evening, we're going to get through, I think, the majority of Chapter 11. We'll still have some ideas, I think, pertaining to phase changes and phase diagrams, but I think we're going to be able to complete our discussion of different intermolecular forces and look a little bit more closely at properties of liquids. Now, before we do that, this evening, I had an opportunity to cook one of my favorite dishes. It's my best dish that I know how to cook without a recipe. It's called carbonara. And I'm curious, when I say carbonara, I want to know, do you know what I'm talking about? Do you know what carbonara is? And I've turned this into a poll question, okay? Is carbonara a blackened fish dish, pasta dish, or a stew? Okay, let me send you a poll question on this one. Carbonara. And this is a two-part question. I want to know, do you know what it is? And at the bottom, have you ever made it? Have you ever eaten it? Have you ever read about it? When I say this is my my best dish, I can cook fancier things, but carbonara is my best one. I don't need a recipe. So if I'm out like traveling somewhere, we rent a house or something, this is my go-to dish right here. Take about 5 more seconds. Okay, we got an overwhelming vote here that carbonara is a type of pasta dish. Absolutely correct. Okay, let me give you the reveal here. It's a pasta dish. Notice as it melts away. There I am with my carbonara and asparagus this evening. So did I have extra time making slides? Absolutely. Okay. I thought that if I really had extra time, I was going to film the making of the carbonara and I'd post that on Perusal. I did not. I sort of regret not doing that. All right, on to chemistry stuff. So we were talking last time when we were beginning to introduce intermolecular forces. We looked at this example of chlorine, bromine, and iodine, molecular forms of each one. And the idea that we had increasing intermolecular forces is that we went from CO2 to the Br2 to the I2. So what we want to keep track of tonight is, as we think about intermolecular forces, we're going to be connecting it to different properties. Let's try to catalog those. What do stronger intermolecular forces correspond to? So one thing stronger intermolecular forces correspond to, they lead to a higher melting point. They also lead to a higher boiling point. So right there, we have two properties, melting point and boiling point, two properties that we can explain in terms of intermolecular forces. Here was some data that we had last time where we were looking at these from F2 all the way down to I2, or our noble gases. And in each of those cases, we were seeing trends in intermolecular forces, trends in the boiling point. Let me shoot you here a question. This one's not about carbonara. This one, if we're talking about intermolecular forces in Br2, what intermolecular forces are present there? This is one, select all that apply. So what intermolecular forces act between Br2 molecules? This ability of having a formula and being able to classify the intermolecular forces that are present, that's something we're going to practice a little bit here. That's, I would say, the most important idea that we have in chapter 11. There's different properties involved, but I think the most important single skill we have is being able to identify intermolecular forces that are present, either from a formula or from a diagram. So within this one, the dominant choice is that London dispersion forces are present. There's a smattering of dipole-dipole or hydrogen bonding. There's also a description here about sigma bonds being present. Thought on that one? I absolutely agree that the London dispersion forces are present. I think that is what's acting between these nonpolar Br2 molecules. The sigma bonding description, I think sigma bonding is within the Br2 molecule. So we want to be careful here. When we're talking about intermolecular forces, these are acting between the molecules. It's not describing the bonding within the molecule. This kind of format right here for the question, which tell me what intermolecular forces act between the molecules, this really sets up well for a multiple choice question. And I know that the distractors here, the incorrect answers of talking about the bonding within the molecule, it seems tempting, but that's not what it's talking about here when it's talking about intermolecular. So we need to be careful with that. All atoms, all molecules, they all exhibit London dispersion forces. So anytime you're asked, well, what kinds of forces are present, you can always check the box for London dispersion forces. All three of these are examples, though, of nonpolar. They have a dipole moment of 0, so they can't have dipole-dipole bonding. And none of these have bonds of an electronegative to nitrogen, oxygen, or fluorine, so they certainly don't have hydrogen bonding. This was supporting the idea that dispersion forces increased as the molecules got larger. And that's exactly what we saw with increasing intermolecular forces there. I looked a little more closely. I grabbed the data for the size of these, the molecular weight, because molecular weight is a really good sort of proxy or shorthand for the scale of the dispersion forces. And it's a really good match where I see F2, Cl2, Br2 with the masses right there going up, up, up. Argon is a little bit more than fluorine, and sure enough, its boiling point is a little bit higher than F2. So in terms of these species that have dispersion forces present, the molecular weight was a really good description for these. Now, what happens if we were trying to put, let's say, HCl on this? So I looked and I grabbed the mass for HCl, molar mass of about 36. So make a prediction for me. Where would you put the boiling point of HCl relative to F2? Is it going to be higher or lower? I'm only giving you two choices here. And as this one comes in, my initial thought is there's no wrong answer here. I can get inside your head. I can understand why you're answering this either way. And the fact that, I can see both of these being plausible, that's telling me, okay, I can understand why this is pretty close to a 50-50 question. It's pretty close to a 50-50 question, because I think that if you say, well, the HCl is going to be lower, you would be saying, well, it has a smaller mass. We've just seen this trend in terms of mass in dispersion forces. So if HCl has a smaller mass, I think it's going to have a lower boiling point. It would have weaker intermolecular forces. But if we look at the experimental data, it turns out it's actually higher. It's not just a little bit higher, it's quite a bit higher. It's about 100 degrees higher. Dispersion forces, they can't explain why HCl has stronger intermolecular forces than F2. Dispersion forces can't explain it. We must have something else going on. Let me send you a poll on that one. So within HCl, tell me about the dispersion force or the intermolecular forces present. What intermolecular forces are going to be present in HCl? We must have something beyond simply dispersion forces, because dispersion forces were not sufficient to explain why it had a higher boiling point, why it had higher intermolecular forces. So again, we're taking the formula and we're trying to think what intermolecular forces would be present. Dominant within here, great job, again, identifying dispersion forces. They are present. You can always check that box. Dipole-dipole requires a polar molecule. We do have a polar molecule here. With HCl, we would have the more electronegative chlorine. We'd have the electron density moving in that direction. So we absolutely have London dispersion forces, and we also have dipole-dipole because this is a polar molecule. Hydrogen bonding, we have a very special condition for that. We need hydrogen that's bonded to nitrogen, oxygen, or fluorine, the most electronegative atoms. Chlorine's quite electronegative, but it's not in that list. It's got to be nitrogen, oxygen, or fluorine. And once again, sigma bond, I think there's a sigma bond, but it's within the molecule. It's not acting as an intermolecular force between the molecules. So in this case, in order to explain why HCl has stronger intermolecular forces, it's because it has this, I would be saying it has a dipole-dipole interaction. We were looking at this last time where we were looking at the different types of intermolecular interactions, dispersion, dipole-dipole, and hydrogen bonding, and looking at examples for when they would be present. So to step through this, a couple thoughts. Dispersion forces, they are always present. If we have atoms, nonpolar molecules, polar molecules, or polar molecules with these special groups, we can always check the box for dispersion forces. Second thought as I look here, within these non-polar examples, they give BF3, CH4. So you can ask yourself, would you be able to determine BF3 and CH4 are non-polar? You've got to be able to have that skill if you're going to be identifying the intermolecular forces present. Similarly, this next group, HCl, CH3CN, could you determine that these examples were going to be polar? You have to do that if you want to be able to identify dipole-dipole interactions being present. And within that last group, once again, sort of a self-assessment. H2O, NH3, would you have been able to determine that those molecules include bonds between oxygen and hydrogen, nitrogen and hydrogen, or hydrogen and fluorine? If so, then you'd be able to identify hydrogen bonding being present. As I look at this, when I say these examples, could you do this? I think it's a skill that you have, but I think you might have to practice a little bit and make sure you're confident that you can do it in that setting as well. as I look with this one, CH3CN, I know that includes both hydrogen and nitrogen atoms, but notice it doesn't have this designation for hydrogen bonding. Why would that be? Can't we just look at the formula? We've got to be able to take the formula and think about, well, what is the structure for it? So even though it includes hydrogen and nitrogen, they're not bonded together. They don't have this nitrogen-hydrogen connection between them. So even though they're within the formula, there is no hydrogen bonding there. It's simply a polar molecule with both dispersion forces and dipole-dipole interactions. Now, what I was doing within this group right here, in order to identify the intermolecular forces present, this is what I think we need to do. We need to be able to draw the Lewis structure, use VSEPR to determine the geometry, and use that geometry to say whether the molecule is polar or not. These were all skills that we were practicing at the start of chapter 9. And these are all prerequisite skills to be able to determine whether we have only dispersion forces, dipole-dipole, etc. I think this is really cool because we're now using this process of Lewis structure, VSEPR to molecular polarity to be able to explain and predict different properties. Chapter 11, I love it because we have so many features of things that are in our everyday world. And many times the explanations for those come back to being able to do these skills that we had in chapter 9. So I really feel, so empowered as a chemist by being able to offer explanations for what's in our everyday world. And so many times it's coming back to the ideas here that we have within chapter 11. Now, if I look within this group right here, it gives an energy value for each of these. We've seen before the energy that it takes like to break a bond. That was like our bond enthalpy value, right? That might be many times 300 kilojoule per mole, 400 kilojoules per mole. All of these are smaller than that. It takes a lot more energy to break a bond than it does to separate out these molecules. Now, if we look at the range of values, because notice it doesn't have just a single value, it has a range of values given. Can dispersion forces ever be greater than hydrogen bonding? Well, let's look at it. Dispersion forces go from very small, 0.1 up to 30 kilojoules per mole. Hydrogen bonding from 10 to 40. So could dispersion forces ever be greater than the hydrogen bonding? It appears so. You could have dispersion forces exceed those of a hydrogen bond. We've talked a little bit about what molecules have large dispersion forces. Recall that information. What kinds of molecules have large dispersion forces? We looked at two features last time. It had to do with a larger molecular weight, and we also saw that the structure could be important. Long chains that were fitting together, sort of like our sandwich that were fitting together, those would be examples of things that would have larger dispersion forces. So it's quite possible that you will have examples like that that overtake these other ones. So let's see if we can sort of think about it. What do you think would have stronger intermolecular forces? H2O or this example on the right, where these squiggles correspond to long chains of carbon atoms in which dispersion forces dominate. So I'll give you a little bit more information. The one on the left, H2O, you're familiar with. The one on the right, this is found in butter. So let me send you a polling question on this one. What do you think has stronger intermolecular forces? H2O or butter? Take about 5 more seconds. Okay, so we got dominant votes here for butter within this. 75 to 25. So majority of folks are saying butter. Now, if I were to look at this, when it comes to H2O, well, I know it has dispersion forces. It's got dipole-dipole because it's a polar molecule, and it also has hydrogen bonding. For the butter, well, it pretty much just has dispersion forces. But I agree with you. I'm going to pick the butter because butter, after all, is a solid. H2O at the same conditions as the liquid. Excellent job. I come back to this point is if you tell me information about the melting point or the boiling point, you're telling me information about the intermolecular forces. This would be something where I need some data. I need to look at it. I need to see one is a liquid and one's a solid. And with those insights, I'm going to agree with you. Great job. I'm going to say that the dispersion forces, they're dominating in this case. Comes back to sort of this idea that I mentioned last time. And this is how I've seen questions asked in the exams for this. If you tell me what the boiling point or melting point is, you're telling me about the strength of those intermolecular forces. Sometimes you're going to be asked to make predictions. It will tell you two different molecules and it would ask, which of these has a higher melting point? Which of these has a higher boiling point? Other times you're going to be given data and you'll be asked to provide explanations. Let me show you what I mean by that, okay? Here I list a series of different molecules. They're all very similar. In each of these cases, they're all tetrahedral. It's carbon with 4 hydrogens, carbon with 4 fluorine, or 3 hydrogens and 1 fluorine, 2 and 2, and 1 and 3. So you see the different setups. So they're all these tetrahedral molecules, carbon in the center. I list the molecular weights there because that's a really useful tool we mentioned to estimate the dispersion forces. So if I were to look at this right away, I'd say CH4, smallest mass within here, that has the smallest dispersion forces. It looks like CF4 would have the largest, if I'm just thinking about the dispersion forces. Let's see how the actual boiling point data comes together. So these first two, CH4 and CF4. Does that make sense? Well, when I say, does that make sense? It depends. What are we including within our explanation? When I look at those two, I can absolutely explain those using dispersion forces. In both of the cases, the only intermolecular force present was the dispersion force. CF4 has a larger mass than CH4, corresponds to a larger dispersion force. Yep, that absolutely explains what's going on. Now, as I extend beyond this, I need you to really pay attention here. See if you can follow my logic. This was the easiest one in the set. Okay, I need you to really pay attention here the next 2 minutes on this. Here's the data for the next, for the CH3F. It has a higher boiling point than the other two. So this tells me this has the higher intermolecular force out of all 3 of these. How would I now begin to explain it? This is in the category of, you give me the data and then I will explain it. I would look at these two. I would say that the dipole-dipole interactions must explain the difference, not dispersion forces. CH3F has both dispersion forces and dipole-dipole. It's got smaller dispersion forces than CF4 though, and yet it has stronger intermolecular forces. It must be due to the dipole-dipole interactions. This kind of question right here, where we are looking at both of the variables that were present that we could use in our explanation and evaluate it, really sets up well for an exam question. This is how that same thing would be set up on an exam. One has a boiling point of 145, one has a boiling point of 194. This is explained by using, is it dispersion forces, dipole-dipole, both of those, or neither of those? It's explained by using the dipole-dipole. Are there dispersion forces present? Absolutely. But it would not serve as part of my explanation because that would have said the opposite was being true. This format right here of being able to consider the intermolecular forces that are present and use those in an explanation, many times I see that on a test. Now, let me ask you a question this way. So I'm not asking about, could you answer this question right here? Because I think it's something we're still practicing. I want to ask, do you understand the format here? Do you understand the format, how it gave you information and then two different things that could be part of the explanation? And the reason I'm trying to take care with that is it's very difficult to answer it if you don't really understand what the format is. This is one where it's giving you the experimental information. It's not asking for a prediction. It's giving you the experimental information, and then it's asking you to evaluate, well, what would be part of that explanation? I think it's a pretty high order sort of logic puzzle for it. Most folks within here, pretty good consensus that you understand what the framework would be. Let me work a little bit and talk through the next two examples here. Here's data for the next two. So as I look at these, the easiest one to evaluate is, again, the dispersion forces, because I can look at the mass. CH2F2 has greater dispersion forces. Could that be part of the explanation? It could be. It has stronger intermolecular forces, higher molecular weight. Could the dispersion forces be part of the explanation? Absolutely. I don't necessarily know which one has a larger dipole moment. I can't look at the formula the same way and say, oh, this one's a more polar molecule or not. You're not going to be asked to do that. I'm sure that you'll be asked to evaluate things like the magnitude of the dispersion forces. So within this one, they're not going to try to trick you and say, aha, tell me about the dipole-dipole. I'm just being honest with you. I don't know which one of these has a larger dipole moment. But I do know that the one with the larger mass has the greater dispersion forces. Let's add the very last molecule in the mix. If I were to look and do a comparison across all of these, first thing I'd evaluate is, well, I know which one has a stronger intermolecular force, and I know which one has the weakest. I know which one has the stronger dispersion forces. I know which one has the weakest. So as I look with that one, it tells me that bottom molecule, CHF3, it's got to have the strongest dispersion forces. It's the largest mass by far, and yet it has the smallest boiling point in the set. That really tells me that even though this is a polar molecule, I got to think it has a smaller dipole moment than the other two. Because it's got the strongest dispersion forces, yet it has the smallest intermolecular forces, the smallest boiling point. It must not be that strong of a dipole moment. That would be my logic as I'm analyzing and putting together these parts. Now, that idea of offering explanations for the property, I think that's one of the most advanced ideas in this chapter. An easier one, if we step back, would be simply identifying the intermolecular forces that are present. To me, this is all about being able to write the VSEPR predicted geometry and think about whether it's a polar molecule or not. If I were to look at this group right here, well, I know they all have dispersion forces because every molecule, every atom has dispersion forces. So that's easy. When I'm thinking about the dipole-dipole forces, the real thing I'm trying to think of, is there an example of one where as vector quantities, the bond dipoles cancel? Is there something where even though I have different atoms present, they would still cancel and result in a nonpolar molecule? As I look at this group right here, well, HBr definitely is polar. CH3F, definitely polar. The only one that I have within here where I have polar bonds and yet they cancel, that would be the xenon with 4-fluorine, because that's back to being a square planar. That's one of our funkier VSEPR predicted geometries. So that would be the only example that I have right here that is nonpolar and only has dispersion forces because the bond dipoles cancel. When I look within the next category of hydrogen bonding, if I first just look and say, well, which of these are examples where I see hydrogen bonded in a molecule that has nitrogen, oxygen, or fluorine, All of these are examples where hydrogen is in a molecule with nitrogen, oxygen, or fluorine. But I got to look a little bit more closely. This is the only one with hydrogen bonding, because remember, it's not sufficient to be in the molecule. It must be bonded directly to nitrogen, oxygen, or fluorine. So this would be the only example here that was exhibiting hydrogen bonding. So within here, I think you can really see, if we're trying to identify the forces present, we got to be able to make a sketch of the molecule. We got to be able to know what the VSEPR predicted geometry is, and we got to be able to determine the molecular polarity. Now, I've cut our table just a little bit here, okay? I've talked about dispersion forces down to hydrogen bonding. There's one more category to add, and that's what's called ion dipole interactions. The example they give here is when you have an ionic solid dissolved in a polar liquid. The example they give is like NaCl in H2O. So this is the only one where we have a combination, right? All these others are looking at specific atoms or molecules. This is the only one where we have two things mixed together, something like NaCl in H2O. What they're describing here is a combination where it's something like this. This is another way we can still have opposites attract, positives and negatives. They're saying, what happens if you take an ion like sodium plus and you surround it by water, or chloride and surround it by water? Notice the water, they're trying to show we have partially positive at the hydrogen, partially negative at the oxygen, and that those can then surround either the anion or the cation. When we write NaCl aqueous, we were thinking about how they were separate from each other, that we did not have a compound of NaCl. Aqueous meant that it had dissolved in the water. To dissolve in the water, it means it's getting surrounded by the water molecules like you see here. The strength of these, this is an important idea, and it's the start of chapter 13. So in Chem 1220, excuse me, the course pretty much picks up at this point, thinking about interactions and making solutions. Way back when we first started the class, we looked at the particle level for what happened, about how an ionic compound dissociated and gave us our cations and our anions. And that if we had a molecular one, like sugar, like sucrose, when we added that, it could still dissolve, but remember we called that a non-electrolyte. It would dissociate, but it was not putting free ions in solution. We've added more insights now based on what we've just been talking about for what takes place here at the particle level. So first of all, this is water. If we show the different partial charges there, I think I have London dispersion forces present, dipole-dipole, and hydrogen bonding holding the water together. When I add NaCl to it, the NaCl dissociates. Notice how it's being surrounded by those positive and negative charges. That's what it means to have ion dipole interactions. The ion is either the cation or the anion, and the dipole is coming from the water. If we take our non-electrolyte like sugar, that was at the particle level, it dissociates again. It's still being surrounded by the water, but we don't have ion dipole interactions because we don't have ions, right? The sugar was not an ion. It stayed together as a molecule. That was our last interaction that we have in the set, and that's always the strongest. We don't have to worry about that being overtaken in some way. So what I grabbed right here, I want to show with you some of the end of chapter problems just to show you the range of how these get asked. So notice this first one. What kind of intermolecular attractive force is present? This is asking what kind would be present. Same here with 1117. What intermolecular forces must be overcome? It's asking what intermolecular forces are present. This is looking at the formula, classifying it, and thinking about what intermolecular forces would be applicable. Is it dispersion forces? Yeah, always. How about dipole-dipole? How about hydrogen bonding? This one right here, 1118. This one's asking what type of intermolecular force would account for these differences? It's starting to give some data and it's asking why. If I'm looking at here in example C, it's giving me information about krypton, information about Cl2. What intermolecular force would I need to account for that? Well, this one's easy. They both only have dispersion forces. So that's what I'm beginning to think about within those. Now, if I move down here, now within here, I have an example about the an additional feature. This example right here, 1123. It's giving descriptions of both of them. It says they both have the same formula, and yet they have different boiling points. How can that be? This, I think what they're trying to get at is back to that example of what would make a dispersion force larger or smaller? For the same molecular weight, the dispersion force is larger when you have these flatter molecules that can fit together, and in these spherical ones, it would be minimized. That would be the point that they're trying to get at here. Notice here, to finish up within this one, two different types of questions. This one at the top, 11.28, is asking you to make a prediction. Predict which of these has the higher boiling point. If I look at example A, for example, propane or N-butane, it's asking me to make a prediction. First variable, I'm going to say, okay, well, those are both nonpolar molecules, largely nonpolar molecules. I know dispersion forces are present. Okay, they're going to be greater in the N-butane because that's it's got a larger molar mass. That's how I'd be looking at that feature. So if I'm making a prediction, it usually has a clear feature that I can latch onto and I can look for when I'm doing my comparisons. The other format, 11.26, when it says rationalize, this is offer an explanation. What explains the fact that they have different boiling point values? Notice within these, you're not being asked to make a prediction. It's giving you the information. It's giving you the boiling points. Therefore, it's giving you the strength of the intermolecular forces. And now it's asking, well, why would this be? All of these questions at the bottom in 11.26, all of these, I think, set up really well for those two-part questions that I mentioned as far as do you understand the format? Because I think all of these, that's exactly would explain, that would exactly fit that kind of format. When it says rationalize, that's what it means. Okay. Now, we've been talking here about intermolecular forces, about identifying which ones are present, connecting them to boiling point and melting point, being able to also, given the data, describe which ones are important within our explanation. That right there, key skills within the chapter, those would be the most important ideas to take away from this. We have other questions in the chapter, other topics, but I know that is the most important topic to address. Let's spend a little time now here looking at different properties of liquids. 3 different properties I want us to think about: viscosity, surface tension, and capillary action. All of these were within the pre-class video. So first of all, viscosity. Viscosity is defined as the resistance to flow. Different motor oils flow more or less easily. Honey is something that has a very high viscosity. You can change the temperature to change the manner in which it flows, but honey has a very high viscosity. It is very resistant to flow. Okay, if you turn over the jar, it just barely moves out. Now, when I say that you can adjust the viscosity with temperature, I looked it up. So you can buy like these warming boxes for your honey. Look at all those honey bears in there. So what it's doing is it's keeping the entire thing warm. So it's changing the resistance to the flow so it can flow more easily out of there. Okay. Now, let me share with you a little anecdote here, a little scenario. Okay. I was at the grocery, true story. Okay. I'm at the grocery and I'm in the bulk food aisle. And there's a guy very similar to this gentleman right here who is helping out another customer. It was a bulk food where you can buy honey. You would bring in your empty bear or your empty container, and they had like a spigot, and you could open it up and you could fill up your bear that way. Okay, that's the kind of grocery store I go to. Okay, some kind of, I don't know, new age health grocery store or something, so I can cook my carbonara. But anyways, at that setup right there, the heating lamp that they had for it had gone out. There's a little burner thing, it had gone out. And so the helper tells the woman, you know, it looks like the lamp has gone out. The viscosity of the honey has decreased. It won't flow as easily. Let me go to the back and I'll see if I can get some more. Now notice the use of the word decreased. Viscosity is the resistance to flow. Viscosity, I find in everyday language, people get completely opposite. This guy got it completely opposite. He said, oh, the honey decreased, now it won't flow as easily. That's completely wrong, okay? Completely wrong. Now, here I am, I'm at the grocery store. I'm standing right next to them when this conversation takes place. So I got a polling question for you. Do you think I'm the kind of guy that when I'm at the grocery store, I talk to other people? Do I keep to myself or do I butt into conversations? You know me a little bit. Do you think I absolutely butt in or do I absolutely keep to myself? Take about 5 more seconds. Okay, pretty strong consensus here that I'm the kind of guy who's going to butt into a conversation. You're absolutely right, okay? When I was your age, I would never talk to anybody at a grocery store. Why would I? I'm just going in there, you know, I'm going to get my vegetables, get my pasta, and I'm all set, and I'll pay for it. Now, I don't know why. I'm the kind of guy that, yeah, I'll absolutely talk to people. I'll recommend chips. I'll recommend, oh, that's a good pasta sauce. You know, I don't know if you've seen these ads about turning into your parents. I'm completely that person now. I would just chat with anybody in a grocery store. I look for reasons to talk to them at the grocery store, okay? So if you said 4 or 5, yeah, you know me pretty well. So here I am. I have just seen someone misuse the term viscosity. He goes to the back and I'm standing next to that customer and I have a teaching moment right now. Do I say, well, you know, that's not what viscosity means. Viscosity is resistance to flow and therefore blah, blah, blah. Or do I keep my mouth shut? I do not know why, but in this instance, I kept my mouth shut. I do not know why I did not use it as a teaching moment. Chapter 11 is full of all these teaching moments. I mentioned this to my wife at the checkout. I said, you don't know what just happened. I was just in the bulk food aisle and someone said this about viscosity and I blah, blah. And you know what? I kept my mouth shut. And she said, that must have been killing you. And it was. I do not know how I kept my mouth shut at that point. All right, moving back beyond viscosity here, okay? Now, within viscosity, here's, I show different molecules. These are all set up in terms of increasing viscosity. These are all increasing resistance to flow. Now, how would we begin to explain this? Well, they definitely have increasing dispersion forces. Larger molecular weight, larger molar mass gives me a larger dispersion force. I also think it's cool how these can be thought of sort of like pasta. And the reason I bring that up, these are all single bonds throughout. And so as a liquid, you know, it's not like it just stays written as this formula right here. If you have single bonds throughout, they can all get tangled up like this pasta. It can give you resistance to flow. It doesn't flow as easily because it's all tangled together. The reason I'm bringing that part up is this, to me, is a really cool feature of organic chemistry. Organic chemistry is not saying, well, here's the formula, let me add it up and do dimensional analysis. Organic chemistry is about taking the molecules and imagining what are they like in 3 dimensions? How do they twist and turn? What does that shape really look like? How do they get entangled with each other? And this is one of the few examples in this class where we can sort of begin to visualize that. So that's how I would explain the increasing viscosity with these. Next one that I want to mention is surface tension. So surface tension is a manner in which a fluid balls up. It takes on a spherical shape. What's going on within this one? Here's a particle level description for it. It's pointing out that if you have, let's say these are dispersion forces. Let's say we have dispersion forces throughout, or dipole-dipole, it doesn't matter. The atoms or molecules in the center of the liquid, they're attracted to all of their neighbors, but the ones on the surface, they're attracted to their neighbors that are in the liquid, but not in the other direction, because there are no neighbors there. So what this means is they're trying to show graphically, it's as if the ones on the surface then almost like cluster back, they get pulled back to the rest of the liquid there. That creates a tension on the surface. So you could even, as you see here with a small insect, even just walk on the surface with that. As I'm looking at this description, I'm seeing in my mind some connections for what was taking place when we talked about real gases. Remember with our van der Waals parameters, we had two different parameters, A and B. A corresponded to attractions, B was the size. The attractions that were present, they made the apparent pressure less than you would have thought, because the molecules that you had within the gas there, if they were attracted to their neighbors, they were being pulled towards their neighbors a little bit rather than striking the wall with their full force. I see the same kind of parallel here. If you're in the center and being attracted to the other ones, that's different than being towards the edge. So that visually in my mind, I'm beginning to see some parallels there. Water is something that has a fairly high surface tension. My hunch is you've seen it bead up like this before. If you've seen liquid mercury, that has a really high surface tension. When you pour that out, it just clusters up and it really adopts a spherical shape. The reason they end up being flattened down a little bit is even though they have a spherical shape, gravity is pressing down on them as well. So they end up looking somewhat like flattened pancakes. Now, I shared this video. There's quite a few examples of folks within the space station when they're looking for things to do. And in this case, it's the astronaut taking the ball of liquid, and instead of all flowing, notice how the surface tension brings it all together because there's not gravity opposing it to flatten it out. So he adds different food colors to it. This part's really cool where he adds a like an antacid. So there's some chemistry going on here. Bubbles are being formed. Occasionally it sort of jumps out. You know, if you're on the space station and you're looking for things to do, playing around with things in zero gravity, this is an example of what you might be led to do. Pretty cool. Now, I found another one from a space station. Okay, let me show you another video from a space station. Also has to do with surface tension. Space station, gravity failure. Okay, so that one obviously not from a space station, even though it's on television, on a movie there. That was from a trailer. I remember seeing that trailer, and my family, they turned to me and they're like, so would that really happen? So again, chapter 11, I have an opportunity to use this as a teaching moment and say, Well, you know what they're trying to describe there? That's all about the surface tension and the manner in which the intermolecular forces of the water, in the absence of gravity, is pulling it so it adopts a spherical shape. Now, do I say it that way? I don't know. I don't even remember if I butted in that way. But my point is, once again, in chapter 11, you're going to have all kinds of information that you can decide to use wisely and inform the general public. You don't necessarily make friends with chapter 11, but you will feel smarter. Now, this one right here, the movie Passengers, I haven't seen it. I don't really think it's a science movie, might be a sci-fi movie, but it did cause me to think, what are my favorite science movies that I would recommend? These are my top 6, okay? Beautiful Mind, Hidden Figures, The Theory of Everything, which is about Stephen Hawking, Imitation Game, The Prestige, and The Martian. So I'm curious, if you've seen one of these or if you have another, tell me in the chat, what's your favorite science movie? All 6 of these are outstanding. As those come in, the one with The Beautiful Mind, that was set at Princeton, I believe. So that he's playing a mathematician, and a good friend of mine here at OSU, he's in the math department, was at Princeton at the same time, and he knew the person that the movie is based on. It's a true story, and not just knew him, they were 2 guys that would go out in the courtyard, share a smoke, because they were like, you couldn't smoke inside at the time. So I thought it was so cool that here he is. He's at OSU now. He's a really good mathematician himself, but he was pals with the character that The Beautiful Mind is based on. I'm gonna track down some of the recommendations you have. Appreciate it. Now, another phenomenon here. This one I think is cool because it shows up a lot in terms of both biology and botany, which is called capillary action. So the idea here is we have mercury that's in this glass tube. It has cohesive forces which correspond to like that surface tension of the mercury being attracted to itself. If we contrast that with water, water is attracted to itself. We just saw that a moment ago where if you put water on the surface, it balls up. So there's attractions from water with other water molecules that are cohesive. But notice with water, you probably saw this in lab, how it has a meniscus that ends up looking like a smiley face. It ends up getting drawn up the sides of the tube. And the reason why is it doesn't have simply cohesive forces of water with other water. There's also adhesive ones between the water and the glass that's on the sides of that. So this balance between what's bigger, is it the cohesive forces or the adhesive forces? That's what gives rise to this meniscus forming in the shape that it has. Now, the book doesn't really tell you, well, what's going on with the glass here? What is glass made out of? The main thing I've researched is I've looked at the structure of glass, okay? Silica glass. That's my most, what I show right here, this is my most far-reaching, highly cited scientific paper I've ever written or I ever will write, where I looked really, really closely at the structure of glass. This is one I did as a postdoc researcher here with Dr. Grandinetti, who's in the chemistry department here. So I know a hell of a lot about silica glass, which is what the walls of these glasses are, the glass container is. And what they're trying to show here is the structure of a glass is silicon surrounded by 4 oxygens. But at the surface of the glass, it gets truncated. It has to stop somewhere. It stops on the surface with the oxygens on the outside. The oxygens there are partially negative. So notice how it's trying to show it here within the water molecules. They're trying to show this attraction between the partially positive of the water and the partially negative of the glass. That's a strong attraction right there, strong enough that it leads to this net attractive as it pulls up right there. This particular feature right here, the textbook doesn't go into it. Just add it to your list if you want of things that you know from chapter 11 that makes you feel smarter. So that's what's going on when we're comparing water, and it's very strong adhesive forces to the sides. With capillary action, this is just really cool. How, imagine, if you will, that the water gets drawn upward due to the adhesive forces. The sides of it go upward. And then in order to minimize the area, what surface tension does, in order to ball up, it's as if the center of it then gets pulled upwards again. Then the outside goes up the wall, and then the center gets pulled up. Then the outside gets pulled up, and then the center gets pulled up. It's this back and forth, back and forth. That's what leads to this capillary action and causes it to rise up a narrow tube. And it's really cool, right? This is what happens with different plants, is it goes up through the membranes within there. This back and forth. And I think it's a really cool application to show how we have the intermolecular forces, adhesive forces, and surface tension all taking place at the same time. Now, if I look at these features right here to sort of summarize back for our properties of liquids, we began our discussion here how about higher melting point, higher boiling point, both corresponded to stronger intermolecular forces. Higher viscosity also goes with stronger intermolecular forces. I'd say the shape of the molecules, remember our pasta example, that could influence it too. But higher viscosity, higher resistance to flow when the intermolecular forces are greater. Higher surface tension, more likely to ball up on itself. So notice right now, everything's easy. Stronger intermolecular forces meant higher, 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 higher. They're all fitting together. Capillary action, I don't really think about it the same way. We don't usually rank something and say, oh, this one has strong capillary action or this one has weak, because it goes beyond just the intermolecular forces. It depends on what the sides of the container are. You'd have different capillary action if it was going with a plastic, for example, or versus glass. There can be differences there. So we don't do capillary action and like do the same kind of ranking right here. But for these other ones, viscosity, surface tension, boiling point, melting point, I think we've got a really clear link between the intermolecular force and those properties. The last one here at the end, and we're going to get started on this, but I don't think we're going to finish it. I want to talk a little bit about another property and what leads to phase changes. So first of all, right here, this is one where we're looking at the vertical axis here. It says the energy of the system. I could think about it in terms of the enthalpy, where we have the solid at the bottom, liquid is higher, and gas is even higher than that. Notice it's showing that you can go from the solid to the liquid to the gas, or directly from the solid to the gas. Those are all examples of endothermic processes. Endothermic because we're going from lower to higher enthalpy. We had to add energy to go from the solid to the liquid, or add energy to go from the liquid to the gas. If we're going down in the other direction, those are all exothermic. Energy is released during that process. Now, I list here the names for the 6 different phase changes. I think you probably know several of these already. So take a second right here. What I'd like you to do is match them up. This is like mastering chemistry, drag them over. First of all, add the endothermic processes to the figure. I see 3 endothermic processes. See if you can add these, make a sketch, put them on whatever you have right here. See if you can identify the 3 endothermic, and then I'll share my work. And I guess when I say add them to the figure, I guess what I'm really saying is we need to know that. We need to know the names of the different phase changes. We need to know that when you go from a solid to the liquid, that will either be called melting or fusion. Both of those are used interchangeably. To go from the liquid to the gas, that's called vaporization. And to directly go from the solid to the gas, that's called sublimation. I brought up an example of that. Carbon dioxide is something that at everyday conditions directly goes from the solid to the gas. It sublimes. Now, we've got 3 other ones now that are exothermic. Take a second, see if you can identify those. 3 different blue arrows. See if you can add those to the list, to the figure. To look at those, going from the gas to the liquids, condensation. Freezing is from the liquid to the solid. I think probably the main one that you may have not heard before is called deposition. Deposition is going directly from the gas to the solid. I've wasted our time enough tonight with different anecdotes, but this is one that oftentimes you can do it in a lab. You can easily set it up where you're trying to get a very thin surface, a very thin coating. So what you do is you start it out so the particles are in the gas, and then you have it so that they then settle and form right onto the surface as a solid. So vapor deposition is what that is called. What I'd like you to have within this one as a learning objective, what I need you to do is I need you to know the name for all 6 of these phase changes. Which one corresponds to vaporization? Which one corresponds to sublimation? I need you to know the name for all 6 and whether it is endothermic or exothermic. So in a way, I need you to know the image that's being shown right here on this figure. Now, if we're looking then at the transformations with these different changes of state, this is something you might have seen before. This is what's called a heating curve. So what this is showing is the vertical axis is the temperature, and the x-axis is they're adding heat. So they're starting here at position A, which would be, in this case, it's for H2O. They're starting out with ice at minus 25 degrees C. They're adding heat to it. As we move along the x-axis, the temperature goes up. There's a plateau here between B and C when the ice is melting. Then the water increases temperature as heat is added. Then there's a very long plateau when it's being vaporized. You've turned it all into the gas, and then it rises up again from there. If we look at these, some of these are different things that we've already sort of used back in chapter 5 to do calculations. This whole diagonal right here, raising the temperature of a liquid, we would use the specific heat of water for that. We would be adding a certain amount of heat. The temperature would change based on the mass and the specific heat capacity of that substance. And for water, if you think back, that was our 4.18 joules per gram K. Those were calculations we did back in chapter 5. If we're having a phase change, that's called the heat of fusion if we're doing the melting, or the heat of vaporization when we're boiling it, when it's vaporizing. One thing to note within those, notice how those values, they don't include any delta T. It's just in a certain number of kilojoules per mole, And the reason why is when you're having a phase change there, the temperature does not change. You're adding heat to it, but the temperature remains constant when you're melting that ice cube or when you're boiling that water. So if we think about this a little bit more deeply, heat is being added, energy is being added. The temperature is not changing. The temperature, remember, that was linked to the kinetic energy. What's happening is we're adding heat, we're adding energy, and it's increasing the potential energy. The potential energy is going up when I go from a solid to the liquid. The potential energy is going up when I go from the liquid to the gas. That's what's taking place along these plateaus. I found this figure that I like because it shows what takes place at the particle level. And I also like it because it's looking at H2O, and the x-axis, they just ran it in the opposite direction. Sometimes students think, oh, this is the shape of a heating curve. It can only look like this. Well, yeah, that's the heating curve when heat's being added. This is what it looks like if you have a cooling curve. If heat is being removed, you could start with the gas, and as you progressively remove heat and cool it, it goes from a gas to a liquid to a solid, which is taking place at the particle level. So with our gas, the particles are quite spread out. Notice what happens when you have a gas and a liquid. When it's beginning to condense, you have both of them present at the same time. During this long stretch, it's a liquid. And then when we have this right here, during the freezing, we've got a combination again. It's progressively freezing, so it was a liquid. It's finding its way from a liquid to a solid. So along the plateaus, you get a combination. Sometimes students say, well, I don't really know how to visualize that. Well, I bet you've seen ice water before. I bet you've seen an ice cube in a cup of water at the same time. You're seeing both of those present at the same time. That's what's taking place when you have both a liquid and a solid present in the container at the same time. So let's think about this a little bit. I want to look more closely at this interaction or the transformation from the liquid to the gas. Okay, so in the kitchen tonight, when I was making my carbonara, I needed to start by boiling water. That's one of the steps. Okay, so in the kit, I told it was a pasta dish. So when I say that's one of the steps, it's not like this is a big secret. Okay, if you're going to be making pasta, yes, you've got to boil water. Okay, you don't need a PhD to know that. Now, this is what happens though. So in the kitchen, the temperature of the water is going to go up and then it's going to boil. As it's going up, well, that would be along this segment right here between C and D. If I use the specific heat of water, I could calculate, well, how much heat did I have to bring it up to the boiling point? And then when it boils, it's along this plateau. That's the energy that it takes to turn it from the liquid into the gas as I go along D and E. Now, what temperature is that going to boil at? Pure water, if I don't have anything else in it, it boils at 1 atmosphere. It's going to boil at 100 degrees C. That's the boiling point for pure water under those conditions. So quick thought on this one. Water boils at 100 degrees C. Look at these children right here. They are standing in pools of water. That water is not going to stay there as a liquid forever. It's going to evaporate. Should these children be warned? Look at this poor soul at the top. He's standing in that puddle of water with bare feet. Is he going to burn his feet? Is it going to be 100 degrees? It's got to be 100 degrees in order for it to go from the liquid to the gas. And yet he's standing in that. How in the world is that happening? Should we put like yellow caution tape around here? What's going on? Let's add this to another thing that we want to be able to explain. What happens right here is we saw that when we had the particular speed for our gas molecules, they weren't all at the same value at the same time. There was a distribution of values. Let's say this blue profile was the distribution of the kinetic energy for the particles. If we increase the temperature, we can see a shifting of that profile. But at any given point in time, some have a very low kinetic energy and some have a much higher kinetic energy. The temperature is a measure of the average kinetic energy. It's not saying every particle has that. Some have higher, some have lower. It's the average is what the kinetic energy is telling us for the temperature. So what happens right here, the way it can evaporate off, even at a relatively low temperature, you can have some that would be above this threshold value, above the amount that they need in order to evaporate and leave. If you raise the temperature, if it's a sunny day, you have even more above that threshold value. But my point is that it's okay to have this kid standing in the water. Evaporation, that's a type of vaporization that's taking place at the surface of the liquid. If the particle's at the surface, if a given particle happens to have sufficient kinetic energy, to be able to leave its neighbors, to be able to pull away, it will. It doesn't come back. So that's how we see over time things can evaporate, even if they're not boiling like this pot of water on the stove. Now, let me ask you this. So if you look at the boiling pot of water there, I certainly see bubbles. So let's say this water has been sitting on my stove for a while. I see these bubbles coming to the top, coming to the top. Let me ask you this one, polling question. What are in those bubbles? If you got your boiling water, is it oxygen gas, air, H2O gas, or simply empty space? Take about 5 more seconds. Okay, so within this one, majority of folks are saying it's H2O gas. I'm going to agree with that. I think what we have within here is, after it's been boiling for a while, all that we have now is the transformation of H2O going from liquid to gas. It's going from H2O liquid to H2O gas. It's this transformation right here. So I don't think we're like breaking any bonds. We're not turning the H2O into oxygen molecules in some way. I think we're just taking them and separating them and pulling them apart. So I think that that's what's taking place. I agree with you. I think that's what's taking place when we're boiling the water. That's what the bubbles are. Now, I try to be careful here when I say, what's the temperature at which the water boils? First of all, I said it was pure water. I didn't want to have other things in the water. I didn't want to make it salt water or have other solutes present. But I also was careful, and I said it was at 1 atmosphere. Standard temperature and pressure is 1 atmosphere. I'm beginning to think about that as it pertains to boiling, because I'm going to expand our description here a little bit. I'm trying to think now at the particle level. In order for something in the water here to go from the liquid to the gas, I think 2 things have to happen. And I'm going to add an idea here. First of all, is I think the kinetic energy of those particles of the water, of the liquid, they have to exceed the attractions that were there. They have to exceed the intermolecular forces that were holding them together as the liquid. Remember that we said that for a liquid, the kinetic energy and the attractions are about the same. And when it becomes a gas, the kinetic energy is greater than the attractions. So that's similar to what we're saying. In order to go from a liquid to a gas, I think the kinetic energy needs to be greater than the attraction. But I think I got another thing I need to add as well. I have to also overcome any opposing gas pressure. What do I mean by that? If I were to blanket that surface of the liquid water, if I would just cover it with a really thick amount of gas, I just really crank in the gas and I just coat it right there, and I got a really high pressure gas above it. It's going to be really difficult now to go from the liquid to a gas because I'm blocking it. I'm putting things above it that is going to block it to go into that space. It's not like it just, poofs there. If I were somehow oppose the pressure, if I make it so I'm blocking it some way, it's going to be more difficult to go into be a gas as well. I'm adding that as another idea. It's not simply the kinetic energy and the intermolecular forces. I'm also thinking a little bit about, is there an opposing pressure present? So let's begin to now think about this. Look at this scenario right here. And this one I stepped through, I really find this to be a helpful visual. Let's see if we can picture this. So what they've done right here is at the top, they've taken ethanol as a liquid. At the bottom, they have an evacuated tube. There's absolutely no gas in there. There's nothing found within that. They put some of the ethanol, they allow it to drain in. What does it do? It goes to the bottom right here, and it begins to vaporize. It begins to go from the liquid to the gas. There was absolutely nothing opposing it. There was no pressure initially opposing it. So it starts to go into the vapor. If you had a pressure gauge on here, it would start to go up because you're starting to put vapor now into the container. You're starting to put gas into the container. This ability of a liquid to go from the liquid to the gas, the more easily that happens, we call that a more volatile liquid. A more volatile liquid more easily vaporizes. It more easily goes from the liquid to the gas. An example, it would be like fingernail polish or acetone, something like that. Okay, you put that, if you've used that, right, you just put it on your skin, put it on your fingernail, you wait a second, and it just evaporates. It was a liquid right there, but it evaporates really quickly, and you can smell it. That's an example of a volatile liquid. A volatile liquid quite easily goes into the vapor. That's a term that I'd like you to know. Now, what happens right here? The liquid is going into the gas. The pressure is increasing there. But I also have examples in this container where the gas now recondenses and goes back into the liquid. Both of these can be taking place. That's what they're trying to show with the arrows. You can have molecules go from the liquid to the gas and then back from the gas to the liquid. There's a back and forth taking place. This idea of them going back and forth, they're not stopping. Both of them are taking place in equal amounts back and forth. That's saying it comes to equilibrium. A dynamic equilibrium where this back and forth still taking place. It doesn't stop. It appears to stop because the two actions are balanced. That's what's taking place here in that scenario. That is a really important idea in Chemistry 1220. It's the most important idea in Chemistry 1220, is looking at different types of equilibrium. Vapor pressure is one type. What does the name vapor pressure mean? Vapor pressure is the pressure in this container being exerted by the gas, by the vapor. If we look at a few details here that I show at the top, as more molecules escape the liquid, the pressure that was in that container increases. The pressure eventually reaches a maximum value. That is a property of the substance. Different substances have different vapor pressures, and it depends on the particular temperature. It doesn't depend at all on the size of the container. If you were to do the same thing and use a different shape of container, different size of container, it doesn't matter. It will still, for that temperature and that substance, it will still reach the same pressure value. It's not PV equals nRT. It's instead depending on these intermolecular forces. Now, the thing that I'd like to leave us with on this one is the magnitude of the vapor pressure. A smaller vapor pressure means you have stronger intermolecular forces. Let's see if we can visualize that. The intermolecular forces we've been talking about, that would be pertaining here to this liquid, if you want to think about it that way. If you have very strong intermolecular forces, it's being held together as a liquid. If it's being held together as a liquid, very little is going into the vapor. It would exert a very small vapor pressure. Or let's think about it the opposite way. Let's say your liquid has really weak intermolecular forces. It's not held together very well as a liquid. It's going into the vapor a lot. If it goes into the vapor a lot, it leads to a higher vapor pressure. I think if we think about what's taking place within those, we can see those features, but we've got to be really careful, because when I'm summarizing the different properties here, stronger intermolecular forces, it was higher again and again. Higher melting point, higher boiling point, higher viscosity, higher surface tension. However, we have one that goes the other way. Stronger intermolecular forces means a smaller vapor pressure. It's a smaller vapor pressure because once again, the intermolecular forces are holding the liquid together, and yet the vapor pressure is talking about what's paired with it, the vapor that corresponds with it. So make sure that you can sort of rationalize that particular feature. Excellent job tonight, folks. I'll hang around for questions. Once again, really appreciate it. We'll finish 11 next time, move on a little bit to chapter 12.
Hey, Dr. Clark, I was wondering why the noble gases have a much smaller boiling point than the halogens.
Well, with several of them, the only one that I did as a comparison was that argon versus F2, and the those are pretty close, those two, and both of those have pretty similar molar masses. I didn't pull up the other ones to see exactly how the molar mass compares with the like Br2 or Cl2. It might also be the case, though, if I'm thinking about the noble gases, those are just going to be spherical. They're not going to be as polarizable. It might be a little bit that the size of the electron cloud isn't as big as if you had an actual diatomic molecule. That would be how I'd begin to explain that.
Okay. Oh, and also, is it, okay, I was just looking at this chart. I kind of missed that there were diatomic molecules for the halogens. So it looks like, yeah, they're about double for most of them. So, and then I was also wondering, why doesn't chlorine form hydrogen bonds, even though it has a greater electronegativity than nitrogen?
Okay, so what we have with the hydrogen bond part, there's sort of two features to it. Okay, what we need to do is we need to have the hydrogen atom's electron go to the more electronegative. And then what we really need to have is to make it so we end up with a really clear, here's the partially positive, here's the partially negative, and that partially negative also, in some ways, the size of it allows the neighboring hydrogen to get quite close to it. And what we find within here with nitrogen, oxygen, and fluorine, they're all quite electronegative, but they're also quite small compared to like chlorine or the ones below it. So spatially, that allows us to have this really clear positive and negative, and then also have it so then a neighboring hydrogen atom can get close as far as the proximity there. So I agree with your analysis about, well, is it simply electronegativity? Electronegativity is really important, but it's also with the nitrogen, oxygen, fluorine being smaller, so they're more spatially, they can get the positive and negative in better alignment, if you want to think about it like that.
Okay, thank you. For the closed container with the vapor pressure example that you gave, is that just if the pressure is 0 and it doesn't vaporize at all, is that still considered equilibrium?
I'll answer two ways. So first way is that even if you take a solid has a very low vapor pressure, but we're going to find it turns out that even a solid, to some extent, does actually sublime and put some of its particles into the gas. Now, when I say some, it's a ridiculously small amount. So even though I'm saying that, you can ignore that feature. The reason I would say that's not considered equilibrium, in order for equilibrium, we want our dynamic equilibrium. It's not the case that nothing is happening. It's a case that we have multiple things happening, but at rates such that they balance off. So we need to have it in that example, both going in one direction and then back in the opposite, if we want to describe that as a dynamic equilibrium.
Okay. And then out of the London dispersion forces and dipole-dipole interactions. Does like, would you say like the length of the molecule is, like if you had a really long one, was that more important than the dipole-dipole always?
I think, yeah, I think that's, I mean, my comparison, if I was doing those, first thing I look at would say, tell me about the mass. And if the masses are about the same, then I'm going to say that the dispersion forces are about the same. If I then have other features like you're describing, maybe it's something that would heighten the London dispersion forces, and I also have dipole-dipole, I'm quickly getting into a space of, you got to give me some data. I've got competing things right here. I don't really know which one wins. You give me some data, and then I will sound smart by giving you the explanation. But I can't really predict the beyond that. So about the only thing I can predict easily is, are the dispersion forces about the same? After that, I quickly get too many competing forces going on.
Okay, that makes sense. And then last thing is, when you're looking at the, is there an opposite of capillary action, or is it the same?
Oh, yeah, I don't, if it goes in the reverse direction, I don't know. Like if I know like Mercury goes in the opposite direction for its meniscus. I don't know if it's called capillary action. If it's, I don't think it's called, I don't think there is an opposite. I think the opposite of capillary action is simply it has very poor adhesive properties relative to cohesive ones. So I don't think there's like a progression, because I think once it balls up in that container, it doesn't necessarily, keep going and going the same way. I'm just guessing on that one. I don't know if they call it inverted capillary action if it goes in the other direction. I imagine an engineer might call it inverted capillary action.
Okay. But I'm trying to understand conceptually why that one, like why Mercury would have a lower like area in the tube, or lower height in the tube.
Yeah, that one, that's the example that's always given. It's not the best for us right now. It's good from everyday experience because we might have seen before how Mercury really has a large surface tension and balls up. It's not necessarily great because it's not clear, well, what are the forces that are involved in Mercury? We don't really classify it quite the same way to say, we don't say it has, for example, dipole-dipole, stuff like that. So it's not great to categorize it. But if we want to think about it right now as it has very strong cohesive forces, it has a very high surface tension. Mercury is very strongly attracted to other mercury atoms. Then I think we could see why it ends up going downward in the tube instead of upward.
It's like the rest of it is, the rest of the mercury that's not on the surface is just kind of pulling it down, basically.
Yeah, I view it like, even though it's in the tube, it's still balling up just like it would if it was on the tabletop. It's still being pulled down into a spherical shape, even though it's in the tube.
Okay. All right, thank you.